an R point. And so then what that means is that you can write 1 equals some polynomial with coefficients from the maximal ideal, and then you start using the equation defining your variety, and you start doing elimination, and you try to eliminate your variable, and you get, while preserving that equation 1 equals something, so you end up with an equation 1 equals something in the maximal ideal contradiction. So that's the general procedure there, and that once you've written the equation 1 as a polynomial with coefficients in the maximal ideal, then it's just formal calculations from there. So want to talk about I guess 2 or maybe 3, depending on how you look at it, reformulations of the valuative criterion. So the convenient definition that you need, and I guess in retrospect, if you look at the old papers, kind of predating this work, that I guess in Colchin's paper, for instance, you could find this, but didn't realize that this is what you needed to extend the valuative criterion to the projective case. So what it's saying is that if you have a point in projective space, and if there is some representative of this projective point, such that all the entries are in your ring, what we're going to care about is maximal delta rings, then we're going to say that it's in V parentheses S here.
Is your S always a subset of some differentially closed field in which you do your job?
Yes. So yeah, I'm just going to assume that, say these are Rit rings, and
are they all in the same differentially closed field?
We can assume that, because we can assume that we're in this large universal domain, kind of containing everything that we care about. Mm-hmm.
Do you have to do that?
No, but I think just for convenience, I guess, or at least convenience for kind of simple-minded bottle theorists doing algebra. Mm-hmm. Yeah, that's so. If this definition is Alice.
Definition seems funny to me from a purely algebraic point of view. For example, if I take a point 1/3, 1/2, 1
mm-hmm.
in P2,
mm-hmm.
that's certainly an integer point,
mm-hmm.
but it doesn't satisfy your criterion.
Let's see. So.
Could you repeat the question, please?
The question is, this criterion seems funny to me because if I get rid of all the deltas, then suppose that I'm just looking at P2 and comparing the field of rational numbers and the ring of integers.
Right.
I'll take the point 1/3, column 1/2, column 1.
Mm-hmm.
It's an integer point because
You
2, 3, 6.
6.
I multiply through by denominators,
Yeah.
but it does not satisfy the criterion there because you can't take. This basically, in essence, says you can multiply through by the denominator of one of the people, but you need to multiply through by both 2 and 3.
Okay.
So is this?
So I mean, so it is well defined. I mean, that's for any represent.
It's well defined, but it's.
Let's see.
Can you say in a couple words why you need this stronger restriction?
I guess
this is not what I would mean by B belongs to B of S.
So I guess the short answer is that this is the definition that you need to make the valuative criterion for projective varieties look just like the valuative criterion for affine varieties. So the statement then
exists a representative.
Like that. Mm-hmm. Right, there exists a representative.
Okay.
So with this definition.
Well, but that's what I'm saying. This is not equivalent to there exists a representative. As far as I can see.
So that.
Because for my 1/3, 1/2, there is a representative, but it doesn't satisfy this criterion.
You have to choose your chart cleverly or something?
Right. So I'll have to think
If you said they're
about that.
representative, I would be happy.
So let's see if if it's awkwardly worded. Maybe that, I mean, 'cause that's kind of usually how I think about it in terms of you're saying that there exists a representative, but we say that if
Reading Jim.
say 0 such that.
Yeah, what do you mean by point projective space? Can you take
So meaning-
representative?
Right. I mean, so right.
Does
So
it say all representatives or?
right. So with all right. So I mean the the equivalence class of these
The
n
criteria
plus
is very
1
hard to
tuples.
understand.
Yeah. That's kind of So you mean in the second case right here, or the original?
one you wrote down.
Okay, so the one in the
V of,
affine case
V of
with
the field is V of R.
right. So in this case, so this is over affine space, right? And so so that there, I mean, there's just literally the coordinates are in.
That's right. That's right.
Literally, so like if you have your point x that satisfies the differential equation defining the
I see.
variety.
You get it. That means there exists a representative. In
Right.
some sense, if you're looking at projective space, you just have to find one representative.
Yes, right. So if for every point, so in projective space, lying on your variety, whichever representative you start off with, if there is some way of dividing by 1, and so basically the reason is that you want to have when you divide it out, you want to have a 1. An entry that's 1, that's non-zero, because you're trying to. The idea is that you're going to verify this positive quantifier elimination result, and so you need to show that that being in the image of something in projective space is preserved. So you're going to have some entry. So so you want to have some entry that has literally something that you're sure that under the homomorphism doesn't go to 0, and so that's the.
So you really do want this stronger thing.
Yes.
You really don't want something like 2, 3, 6.
Right.
Oh.
Exactly.
Wait. For the criterion in projective space, what's the criterion in projective space? Then?
So written the exact same way, but using this definition of P in VR, using this definition on the top. Okay. So it's chosen so that you're sure that because when you divide PI by PI, you get a 1 in that slot, and so because formulas don't know about projective space, they're just
right.
So what you're saying is that you need a representative of the point in the projective space
that has
all coordinates in S.
And one of them is 1.
One of them is 1 or a unit in S. Or
yes,
like that.
exactly.
Okay, interesting.
So,
There should be a big red warning there.
right. Oh, yes. That's
yes, definitely.
It's yeah, that's true. It's not. It's not clear why you want that extra condition there, but. This is the version in P1, which is where most of the examples live anyway. So boil that down, then you can assume that a representative.
Yeah, you got your 1 in there already.
Yes, so got that, and then that amounts to either the other representative is in R or 1 over X is in R. And so this is how when it's written this way, then Morrison's statement about elements that satisfy linear differential equations is gift wrapped to show that projective closures of linear varieties, at least in one variable, are complete. It's exactly what it says.
Well, that seems strong.
So.
You're going to post your slides, aren't you?
Yeah.
Yeah, good.
So say a word about the proof there. So forward direction, use the contrapositive, show that if you have a bad point, then you can construct a counterexample to completeness. And so what is going on with the second formula, so it's a projection, the index set I is just the set of a non-zero coordinate entries in your projective point, and the PIs are what equations that you get when you suppose that you've got a bad point. So since you've got a bad point, then you've got witnesses equations of the form 1 in mx, or m1 in the second case, 1 in m1 over x. So you clear denominators and you get these homogeneous PI. And so that's those are just witnessing the equations that you get from a supposed witness of a bad point. And then you just show using the homomorphism, this underline that's making this maximal delta ring maximal, or the underlying homomorphism, maximal homomorphism, that because the differential ideal is exactly the kernel of this guy, then you can write an equation like this and apply the homomorphism, and then they'll kill everything on this side and keep the one not, so you get something that's false. So get an equation that's false. So that's how you show that this guy is not equivalent to a positive quantifier free formula. So and then in the other direction, then it's exactly Van Andrie's argument for his algebraic in the algebraic case, except that when you get your maximal delta ring, it's not necessarily a evaluation ring anymore, but the replacement for having a valuation ring is that your is that the constant is that the k points descend to r points. So I'm not sure, I could maybe say a little bit more about that later, maybe just in the interest of time. Just say that the hypothesis is exactly what is the part of what we need from a valuation ring, so that if that holds, then we get it. So that's the projective version of the valuative criterion. A couple of other versions. So unfortunately they start getting more and more ugly, but in some sense they're nicer because they eliminate reference to these maximal delta rings. So just going to state it in the P1 case. The statement for n-dimensional projective space is similar, but a little uglier. So basically what's going on here is that a projective differential variety is complete if and only if, for a certain restricted class of subvarieties of the product, that they're images that the Colton closure of the projection does not contain the origin. And so the classic example in the algebraic case of why affine varieties aren't complete is the hyperbola, and then projecting you miss the origin. And so that's kind of what you should be thinking about through all of these subsequent examples. Basically, that's what the middle lines are talking about, that if you have witnesses of a certain form, and the reason why these are chosen, the proof has to do with, again, with the valuative criterion, and witnesses that look like that, what being a bad point looks like. So you're complete if and only if the closure does not, of the image does not contain 0. And so again, we can assume that the second factor here is affine.
William?
Yes.
Would it ever be the case, suppose you're working on the line, over ordinary differential fields, would it be possible, suppose you had a variety that's not irreducible, is it possible that the general component of Ritz could be delta complete and not the other components?
That's an interesting question, and I'm not certain what the answer would be for that. Seems like I guess my initial response is that it could be possible, but right. So the irreducibility generally doesn't come into any of these criteria. So.
But a related question is related to the low power theorem. Is that he answers the question when he can. Is zero a zero of the general component? So if you look at some of your differential polynomials, he has a criterion that often depends on the power to which the order zero indeterminate is raised. So using the low power theorem, if you're just looking at the general component, you might be able to use it to get an answer to your question. If zero, strangely enough to you, or all of us, resides in the general component, then it might answer some of your questions. The projectivization would also lie in the general component.
Oh, yeah, that's a good point. I'll definitely follow up on that. So
might be a help to use the low power.
Okay. Yeah.
It's almost never used.
No, that's yeah. It's a shame because it is a powerful result. So.
But here, I should think it would come in beautifully here.
Okay. Yeah. Definitely. So. Promised you a more syntactic version yet, so this is kind of more geometric, that doesn't mention maximal delta rings. So here if you just look at differential ideals, then if you look at differential ideals generated by polynomials of this special form that are in this upper form, then you're complete if and only if the elimination ideal has a polynomial with a non-zero constant term. And so that's, again, all very similar to the sorts of computations we've been doing. And maybe we won't say too much about the proof of it, other than that it uses the geometric version about the origin being in the closure of the image. So it's almost immediate. So I think maybe just again in the interest of time, because we're out, you said quarter till. So I'll say that there's kind of a funny reduction from differentially closed fields to complex algebraic varieties that I guess has more geometric flavor still in this, that you can phrase the valuative criterion in terms of asking whether a certain sequence of complex algebraic varieties has an asymptote. So we can talk about that maybe afterwards.
That's very close to Ritt's arguments in the low power theorem.
So that might be interesting to chat about afterwards. I would like to say something about an argument that's in a recent paper that I collaborated on with James Freitag and Omar Leon Sanchez. Apologies, gonna scoot off from this one, but we come back one. So this is just explanation of why that example of Poisson is actually complete. And so the connection here is with the differential catenary conjecture. So here's kind of a classical result in algebraic geometry. If you have an irreducible affine variety and of dimension n, and you start at any point on the variety, that then there's going to exist a chain of irreducible varieties starting at the point and ending at the variety. Now, you can state something similar in the differential case, but in this case it's wide open. Instead of having just finite chains that they talk about long gap chains where in between, so if you have differential dimension D, that's in between you've got so infinite descending chain of prime differential ideals. So that is wide open, but whether or not that is the case. But there's a weak form of it that is actually helpful to bounding the complexity or bounding the dimension of possible counterexamples to completeness. So this version is that if you have an irreducible positive dimensional affine differential variety over a differentially closed field, and you have a irreducible zero-dimensional subvariety. So I don't know, maybe I should write on that board better for...
So by dimension, you always mean differential dimension?
Yes, Sorry?
And you want V1 to be positive dimensional?
It's not necessarily. It could be or it couldn't be.
Oh. Well,
So it's just proper, so the dimension goes down.
Not the differential.
Wait.
The
Okay, one of the W's in the conclusion should be a V. Which one?
let's see. I believe so. Let's draw the picture and figure out what the statement should be. So you have your positive dimensional variety V, zero-dimensional subvariety W. Claim is that there is a proper differential subvariety, the V1, that intersects W.
And you said
And that is
positive dimensional?
What about the
it-
next dimension?
If not, I can just take V1 to be equal to W.
Yeah.
Right, but it's not contained in W. So that's why the V1 is not.
Right.
That's the point of the second part. So I guess
Or
there's
W
two
is not
propers
contained in
here. V1 is a proper subvariety
Oh,
of
so you
V,
want both, I
and they're
see.
both. This is irreducible. This is irreducible, and so it's a proper subvariety there, and it intersects W. So this is a consequence of the catenary conjecture.
So it could contain W.
It could contain W, that's correct. But it's not contained in. Mhm.
See, you could.
So,
Hey, what?
and so the importance then of this is that you can perform this iteratively. That you look at this new intersection, zero-dimensional, it's non-empty. This guy, if he's positive dimensional, then repeat the argument. You're going to have a proper subvariety of him that intersects still and go down. And so eventually you're going to end up at zero-dimensional.
So eventually you end up with the zero-dimensional subvariety that sort of crosses W in a funny way.
Right. Mm-hmm.
But, you could have lots of zero ones going down, 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 and stop. I see. So you end
So,
when you go down.
so I mean, it looks kind of funny, but we'll see what it's good for in this context. So, assuming that this weak catenary conjecture holds, then your projective differential variety V is complete if and only if this projection is a closed map for second factors that are zero-dimensional. In the definition of completeness, that there's no restriction whatsoever. It has to hold for all possible y there, and so let's see why this is the case. So it's proof by contradiction. You suppose that there are no zero-dimensional counterexamples, but that there is a counterexample that's positive dimensional. And in this case, then just follow the picture there. repeating the application of the weak catenary property. And eventually you're going to end up with a zero-dimensional, well, V1 there. Now we have to show that it actually witnesses incompleteness, but this is sufficient because we're supposing that there are no zero-dimensional counterexamples. So what do we have to do? Well, it's you want to use something that's a little stronger than just the fact that that it's not complete, that you have a positive dimensional y where the projection is not closed. You actually want to you can actually show using Freitag's version of Bertini's theorem that holds over for differentially closed fields, that there's going to be a positive dimensional counterexample such that and a closed set of the product such that the projection, the image is not only not closed, but also that the closure is positive dimensional. And when you look at the closure of, well, the closure taking away the image, that is zero dimensional. So the superscripts start getting a little fussy, and but it works out. So we have basically a bad example. So we have this closed set in V cross Y1, where this is positive dimensional, and it projects down to Y1, and Y2X contained in there is not closed and satisfies a few other things. Satisfies a few other conditions. And so those are necessary to get our contradiction. Okay. So right. Oh, so we had the Y1 that starts off like that. So if we have a bad counterexample, then we have this X that does that. Now repeat the weak catenary conjecture until you have down here in Y1. Here you have the non-closed Y2X, and then in its closure we have this set Y prime that satisfies the catenary conjecture. So what you want to do at this point is look at the restriction of your the set X to the product of V with this zero-dimensional subvariety, and we're going to show that its image is not closed, and so that provides the contradiction. So again, a contradiction within a contradiction. Suppose that it is closed, and then have to do a little bit of staring at the symbols to make sure to verify that all these things work. But what the upshot is that because we're working with constructible sets, you can show that this image is a proper closed subset of Y prime. And so Y prime is supposed to be irreducible, so if we can find something else that's also a proper closed subset that together makes the whole thing, then we're done. And now use the hypothesis Y prime is not contained in that zero-dimensional W that we defined on the previous slide, and show that that we have a decomposition of it given that assumption. So In that case, we've found zero-dimensional witness to incompleteness, contradicts what we started with, and so. Yes, it's a little hard to say whether or not this reduction actually helps in finding concrete examples of incompleteness. But I think given the difficulties of finding particular examples, that reductions like this can only help. So I think that's pretty much what I have time for. You can maybe ask about this afterwards if you like. It's in a different vein related to logic and differential algebra, but not model theoretic, I guess, in nature. And the basic idea is that looking at formal proofs in algebra, that you can sometimes extract algorithms out of non-constructive proofs, and so Henry Tausner and I are interested in seeing what happens when you apply this technique to things like the basis theorem in differential algebra. So very much preliminary type work, but there should be able to say something. So I think I'll end there, and thanks for your questions and suggestions of things to look at. I think I think there's still some more to be said about this problem. So.
Any questions? Are we meeting at 2?
Sure.
Good.
Okay, thank you.
Isn't there any logic workshop? No.
There's no logic workshop.
And is it Aschenbrenner speaking?
No.
Oh, he's not.
He's talking in quite a few weeks.
Oh, it was May.
Yeah.
But there's no model theory?
The model theory talk is about how much foundations you need for Fermat's theorem.
Oh.